All right, workshop 4, give the mechanisms and the products for the reactions below. So a lot of times I'll give you the products, but I just want to make this a little bit harder, practice a little harder than we're doing in the tests. Alkene, HBr, pi bonds nucleophile, pi bond reacts with hydrogen, breaks the HBr bond. You have a carbocation, the more substituted carbon because it's stabilized by hyperconjugation. So tertiary carbocation, no polar protic solvent, Br minus goes there and adds in. Last thing we ask ourselves, did we make an asymmetric center? So we have sp3 hybridized with 4 different things, methyl, methyl, ethyl, and bromine, so we did not make an enantiomer. Those are all, there's 2 of the same things. All right, another pi bond reacting with HBr, right, breaks the hydrogen bromine bond, makes a carbocation on the secondary carbon, the more substituted carbon. But again, if you have a carbocation, can they rearrange? Yes. You gotta be looking for more stable carbocations, so more substituted or allylic or benzylic. So in this case, you can do a methyl shift, an alkyl shift. That's going to go from a secondary carbocation to a tertiary carbocation, which is more stable because of hyperconjugation. Again, no polar protic solvent, just the Br minus. So lone pair from bromine goes there. Gets our final product. Again, we ask ourselves, did we make any enantiomers? Did we make any asymmetric centers? We did not. This carbon has 2 methyls and this one has 2 methyls, so there's no sp3 hybridized atoms with 4 different things. All right, moving on. So those are those hydrohalogenations. These are acid catalyzed hydrations. Got to be able to draw out H2SO4, the whole structure. You should know that Lewis structure by now. Pi bond reacts with H, gets the O minus there, stabilized by resonance. We're in polar protic solvent. We make a carbocation, the more substituted carbon, that's going to react. When that reacts, that's going to form a positive charge here, right? Make sure we don't lose hydrogens or methyls or any of those kind of things. And it's acid catalyzed. What do you know if something's catalyzed? That means you need to regenerate the catalyst. You're not done until you've regenerated the catalyst. So the O minus here, the lone pair, comes and takes that H, and we make this alcohol. Again, do we have anything that's sp3 hybridized with 4 different things bound to it that we made? No, there's 2 methyls here. So no enantiomer here. All right, for this one, it's a little tricky. There's actually 2 routes you can go because either carbocation you make is going to be secondary, so there's really no preference. So I'm going to show 2 routes. So there's an OR here. So there's 2 routes this could go. The first route I'm going to show is if the H went to this carbon and we had a plus charge on this secondary carbocation. Now if we have a plus charge here, we're going to do a hydride shift to make a tertiary carbocation. Again, acid catalyzed, there's the polar protic solvent, methanol. The solvent's going to react. Solvent's going to react. Notice methyl and H don't leave. Don't skip steps. Don't skip steps. You're going to deprotonate. This is acid catalyzed. Going to regenerate H2SO4. We're going to add the ether here. Now again, did we make any sp3 hybridized atoms with 4 different things bound to them? We did not. There's symmetry here. So this is not an enantiomer. No enantiomer here for this one. All right, the alternate route, another way you could have done this, and you wouldn't know which one to do. So, all right, this is the way this question is designed. You could have a secondary carbocation here, which is totally fine. Right? At this point, there is no ability to do any rearrangements because it would just be making another secondary carbocation. Remember, when we do rearrangements, we only go to more stable. So that means you go from secondary to tertiary, or something that's allylic or benzylic, or could have lone pair resonance. Methanol reacts. We regenerate the catalyst, deprotonate. Now in this one though, notice when this adds in, right, this is making an sp3 hybridized atom bound to 4 different things. So the solvent could come from the top or it could come from the bottom. And because they're already an existing stereocenter that's starting the molecule, you actually don't make enantiomers, you make diastereomers. One thing's the same and at least one's different. So in this case, you actually make diastereomers from that route. All right, moving on. BH3, step 1, NaOH, H2O2. So this is that anti-Markovnikov, way to add an OH and an H in a syn fashion, but an anti-Markovnikov. So the OH ends up on the less substituted carbon. So here, 2 arrows, pi bond reacts with the empty p orbital. The H, the BH bond, the H goes there. See the syn addition, right? The boron on the less substituted. A lot of folks keep, right? What you draw here has to match what is drawn up here. Right? If these are two methyls, these need to be methyls. If this is an H there, that needs to be an H. You can't just draw a blanket, like a random one, right? You got to make sure you match your alkenes or alkynes. That adds. Second step, you don't need to know the mechanism for. All it is the BH2 being replaced by OH. So you see that anti-Markovnikov addition being added there. Do we have an enantiomer here? Do we make one? So there's two methyls there. OH. I think we did. Plus enantiomer. Because OH, methyl, H, then this is like an isopropyl group. So I think we did. So we'd have plus enantiomer as well. All right, moving along. Now mercury. So mercury, two steps, mercury in water, in this case, in water, and sodium borohydride. This is a way to add OH and H or OH and solvent, whatever the H and solvent in a anti-fashion, but on the more substituted carbon. 3 steps there, no carbocations are formed here. The solvent, whatever the solvent is, the polar protic solvent, reacts with the more substituted carbon, SN2-like. We have a deprotonation. Now you have the mercury on there. Last step, NaBH4, all that does is replace the mercury with the H. We again check to see if we made an asymmetric center, something that's sp3 hybridized with 4 different things. Not there, but here we did, so we put plus enantiomer as well. Again, alkene, Br2, polar aprotic solvent, so the solvent will not be involved. How many arrows in that first step? 3. Pi bond reacts, breaks the bromine-bromine bond. Bromine comes back. No solvent involved, so the other Br minus reacts with the more substituted carbon. We get that trans addition. Do we get any enantiomer here? Let's see. 2 methyls there, no. Methyl, H, bromine, and isopropyl. Should we have an enantiomer? Yes, we should. Plus En. Very good. Same exact reaction, only has changed. I use Cl2, but that's basically reacts same as Br2. But I've changed the solvent to be a polar protic solvent, so now the solvent will be involved. 3 arrows, no carbocations. Right? I flip this around, make sure you go to the more substituted carbon. Solvent reacts, SN2-like. See the trans relationship. Deprotonate. We check. Looks like we have plus enantiomer, chlorine, H, methyl, and this. That's 4 different things. An sp3 hybridized atom, so we have the enantiomer as well. So let's be cognizant of the solvent when you have carbocations and when you don't. All right, last 2. H2, we know this is a syn addition with any of these metals. This is a reduction adding hydrogens. So we could either add the hydrogens from the top or we could add them from the bottom. But either way, we're going to make both of these, and these are diastereomers to each other. Right? One center is the same, and 2 are different. So I didn't draw the H's in, but you can see, right? If these are up and wedged, the H's are hatched. If these are hatched and down, the H's are wedged. So they add syn. So we make diastereomers here. For this one, O3, every pi bond gives 2 carbonyls. A good numbering system helps here. So every pi bond would turn into a carbonyl. So you just split there and number your atoms. You get these 2 carbons or 2 pieces, 2 molecules. So 2 pi bonds, 4 C double bond O's at the end. Number your atoms.